Hello, I'm your host, Dr. David Urban, and I will be guiding you through Brown and Poon's Introduction to Organic Chemistry, 6th edition. The slides were downloaded from the Wiley Instructor Companion site and are copyrighted by Wiley. The commentary is my own. I have divided each chapter into smaller sections to make it easier to view on a wide variety of platforms. So let's begin. We will continue with Chapter 3, Part 3, Alkenes and Alkynes. So as we learned before, we can now name them. We see that they have isomerization, and we see that they have a hybridization of sp2 hybridized carbons in them. But what we also know is that they are non-polar compounds. The carbon-hydrogen bond and the carbon-carbon bonds tend to be fairly non-polar. And as such, they only have weak attractive forces between their molecules, and these are called dispersion forces. Therefore, the physical properties of alkenes and alkynes are similar to those of alkanes in the fact that it's all about the number of carbons they have and whether or not they're branched. Most of them have are liquids at room temperatures and are less dense than water. They tend to dissolve in other hydrocarbons, but not into water. Okay. One of the interesting differences between the alkenes and alkynes is because the carbon is sp2 hybridized, the hydrogen on alkynes tends to be more acidic than that of the alkenes or the alkanes. Remember when we were looking at Lewis acids and bases, the pKa of the hydrogen on ethane is about 51, okay? But the pKa of the hydrogen on an alkyne, the terminal alkyne, is about 25. That means it's much easier to remove that hydrogen than it was for the alkanes, okay? It still takes a very strong base to do this, okay? Remember, as we increased our base strengths, we went from oxygens to oxygen anions, nitrogen, and nitrogen anions. So we actually are one of the strongest bases with an anion on nitrogen and sodium amide to remove that hydrogen. So when we remove that hydrogen, we end up with the acetylide ion. The acetylide ion is a weaker base than the amide ion before, and therefore the equilibrium is shifted in this direction here. Okay, because the water is more acidic than the acetylene, we cannot form the acetylide ion in the presence of hydroxide. Because if we used hydroxide here to pull off this hydrogen, it would generate water. Water is a stronger acid than the acetylene is, and therefore it would shift the equilibrium back in the other direction. So we can't use the strong base of a hydroxide or an oxygen anion. We must use the stronger base of a nitrogen with an anion on it. Okay, so if we look at the pKa values for alkynes, alkenes, we also see that it takes really, really strong bases to remove them. So if water has a pKa of approximately 15.7 and acetylene has a pKa of 25, means we cannot remove that proton with hydroxide. As such, going from an sp hybridized carbon to an sp3 hybridized carbon in an alkene, there's another increase in that basicity or a decrease in the acidity of that hydrogen, meaning we have to even use a stronger base to remove that hydrogen. And of course, the least acidic of the set is the one with the pKa of 51, which is the hydrogen on our ethane. Okay, so how do we account for the acidity of the hydrogen at the end of an alkyne compared with those of an alkane or alkene? And so what we have to do is focus on the stability of the anion formed from each of these, okay? The lone pair on the electrons of an alkane lies in an sp3 hybridized orbital. there's only 25% of that orbital has S character. Remember, the S is more spherical shape. And so it's a very small expansion of that lobe. In the alkyne, we have an sp2 hybridized orbital, and that has about 33% of it is that S character, or a slightly larger bulk to hold that anion. And in an alkyne, we have 50% S character. Remember, those are almost completely round with a small group on it, and that gives us that. So the sp hybridized orbital can stabilize the negative charge better than an sp2 hybridized orbital, and an sp2 hybridized orbital can stabilize the negative charge better than an sp3 hybridized orbital. That's why the acidity increases from a pKa of 25 to 44 to 51. Okay, so that greater S character bears more of the negative charge. Therefore, sp having half of its character S can stabilize more of that negative charge. Okay, so in summary, alkenes and alkynes both have pi bonds. Okay, that means an alkene has one sigma bond and one pi bond. An alkyne has one sigma bond and two pi bonds. We went over adding to the different rules from alkenes, alkanes. We've added alkenes and alkynes. We've also added the EZ/cis trans isomerization of alkenes. And we saw that alkynes have the most acidic hydrogen of all the